The following presentation will thoroughly discuss a popular protocol known as segment routing, or SR. SR is designed based on source routing to forward data packets on the network. It is classified into two types. Segment routing MPLS, or SR-MPLS, is based on the MPLS forwarding plane, whereas segment routing IPv6, or SRv6, is based on IPv6 forwarding plane. This presentation will be focusing on SR-MPLS. I will break up the content into the background, implementation, tunnel establishment, service applications, and reliability of SR. The methods of building large-scale networks and transforming existing networks into SR networks will also be covered. As is already common knowledge, SR can replace MPLS on the control plane, and although MPLS is an excellent protocol that is widely used on live networks, it still has some issues. Let's delve further and examine some of these problems. MPLS involves two protocols, Label Distribution Protocol, or LDP, and Resource Reservation Protocol, Traffic Engineering, or RSVPTE. LDP does not support path computation. Instead, it distributes labels based on IGP path computation results to obtain label forwarding paths. In doing so, LDP has the following advantages originally provided by an IGP. 1. Supports the shortest path first algorithm. 2. Supports equal cost multi-path load balancing. 3. The configuration is simple, making it easy to build large-scale networks. However, LDP has the following two major problems. 1. A large number of messages need to be sent between devices to maintain connection status, wasting a lot of bandwidth and CPU resources. 2. LDP and IGP status must be synchronized to avoid traffic black holes. Take the following topology for example. Assume that A to B is a primary label switched path, and A to C to B is a backup LSP. If the primary LSP fails, data traffic will be switched to the backup LSP. When the primary LSP recovers, data traffic will be switched back. In this case, if IGP path computation results are not synchronized to LDP, the primary LSP may fail to be established for a period of time, interrupting the services that need to be forwarded through the LSP. Next, let's examine RSVPTE. RSVPTE provides multiple functions, including explicit path planning, bandwidth resource reservation, and link protection. However, it poses the following problems. 1. The configuration is complex. A unidirectional RSVPTE tunnel requires more than 20 basic configuration commands. For a small full mesh RSVPTE network with only 4 devices, tunnel configuration needs to be performed 3 times on each device, 12 times in total. If another device is added to the full mesh network, each device requires you to perform tunnel configurations 4 times, raising the total to 20 times. Clearly, this kind of complex configuration will make network maintenance very inconvenient. 2. Due to the fact that RSVPTE is a stateful protocol, neighbors need to send a large number of messages to maintain neighbor and link status, consuming a large amount of bandwidth, CPU, and memory resources, especially when traffic is heavy. If transit nodes, for example P nodes, exist on the network, and traffic on the nodes is heavy, the network may encounter a performance bottleneck. Because RSVPTE is difficult to maintain and consumes a significant amount of resources, it cannot be used to construct a large-scale network. Why is it impossible to deploy RSVPTE on a large scale? RSVPTE adopts a distributed architecture under which each device knows only its own status. If a device wants to know the status of its neighbors, it must send a large number of signaling messages. The next question to present is whether it is possible to get rid of the preceding issues by deploying a centralized architecture in which only one node is responsible for centralized control and unified path computation, and the other nodes are dedicated to traffic forwarding. This is an important concept of SDN. To achieve SDN, researchers from universities initially designed a revolutionary network based on OpenFlow. Such a network is ideal, but the design target is difficult to achieve. OpenFlow needs to deliver a large number of following entries, leading to a performance bottleneck in the delivery rate. In addition, existing devices cannot afford to process the massive flow tables involved in OpenFlow. Upgrading or replacing the devices on a large scale is costly and may even disrupt the existing network. Therefore, OpenFlow is not well accepted by operators on live networks. An SR-based incremental network has the following characteristics. First, existing protocols are extended, achieving smooth network evolution only through device upgrades. Secondly, there is a trade-off between centralized control and distributed forwarding. Thirdly, the network can quickly interact with applications. To promptly meet a service requirement sent by an application, the controller and forwarders perform path computation and data forwarding, respectively, achieving a service-driven network. Let's move on to discuss how SR is implemented. SR is used to divide a network path into several segments and assign a segment ID or SID to each segment and forwarding node. The ingress arranges SIDs sequentially into a segment list, forming a forwarding path. There are three types of SIDs. Firstly, a node SID is allocated to a loopback interface address of a node and can be used to identify the node. For example, we can allocate node SIDs 101 through 106 to nodes A, B, C, D, E, and F, respectively. The second type is adjacency SID, which is allocated to an adjacency on a network. For example, node B can allocate SID 201 to the B to A adjacency, SID 203 to the B to C adjacency, and SID 205 to the B to E adjacency. The third is called the prefix SID, which is allocated to a network prefix. For example, we can allocate prefix SID 16,100 to a network. Although SIDs are expressed in the label format, they are essentially network instructions. After SIDs are allocated, they are propagated through IGP messages, so that each node on the network knows all SIDs. The ingress can then orchestrate paths based on these SIDs. For example, if traffic needs to be transmitted from A to C, node SID 103 of C can be used to instruct traffic forwarding. If traffic needs to be transmitted from A to the network connected with C, prefix SID 16,100 can be used to instruct traffic forwarding. Prefix and node SIDs both instruct traffic to be forwarded along the shortest path established using an IGP. If equal cost paths exist on the network, load balancing can also be performed. The mode in which a single seed is used to instruct traffic forwarding along the shortest path is called segment routing best effort, or SRBE. SRBE implements shortest path forwarding that is used in both traditional IP forwarding and LDP forwarding. In addition, multiple seeds can be combined to form forwarding path. The combination indicates constraint on the path, enabling the path to meet TE requirements. We call this mode SRTE. There are three seed combination methods. Method 1. Combine multiple node seeds. Method 2. Combine multiple adjacency seeds. Method 3. Combine node and adjacency seeds. Let's take traffic forwarding from A to F as an example in which we combine adjacency seeds. Assume that adjacency seeds 112 and 506 are allocated to the A to B and E to F adjacencies, respectively. A label stack can be formed based on the A to B to E to F path, where the first hop is 112, the second hop is 205, and the third hop is 506. The path formed using adjacency seeds is strictly specified. That is, traffic must be forwarded from specified outbound interfaces along specified links. This type of SRTE is called strict SRTE. Another method is to combine node seeds. For example, in the direction from A to F, node seed 102 of B can be used as the first hop, node seed 105 of E as the second hop, and node seed 106 as the third hop. In this way, a forwarding path is formed. Compared with the first method, if there is a more efficient path between two nodes, this method allows traffic to be forwarded through that path or an equal cost path. The forwarding path formed using this method is not strictly specified. Therefore, this type of SRTE is called loose SRTE. The third method is to combine node and adjacency seed. For example, in the direction from A to F, we can use node seed 102 of B as the first hop, adjacency seed 205 of B to E adjacency as the second hop, and node seed 106 of F as the third hop. This method combines both strict SRTE and loose SRTE. Only some paths on the network are strictly specified. For all others, traffic can either be forwarded through the shortest path or be load balanced. Now you know the fundamentals behind the basic forwarding mechanism of SR. Let's compare SR and MPLS. First, let's compare seeds with labels. Although seeds are also labels, they represent forwarding instructions. For example, node and prefix seeds instruct a device to forward traffic through the shortest path or equal cost path, while an adjacency seeds instruct a device to forward traffic through a specified outbound interface. Second, we will look at SRBE compared with LDP. SRBE is an IGP extension. As it requires less protocols, it is simpler than LDP and avoids the IGP-LDP synchronization issue. Finally, let's examine the differences between SRTE and RSVPTE. SRTE is also an IGP extension, and it requires less protocols than RSVPTE. SRTE orchestrates paths on the ingress, and transit nodes do not maintain network status. Therefore, The transit nodes do not need to send signaling messages to each other, mitigating the excess consumption of resources. This makes SRTE more suitable for a large-scale network. An additional advantage of SRTE compared with RSVPTE is that if SRTE uses node seeds, the path indicated by the node seeds support load balancing. It's time to discuss the establishment of SR tunnels. An SRBE tunnel can be dynamically generated by an IGP. This configuration is simple. As for SRTE tunnels, they can be established using three methods. Method 1. Manual configuration. Manual configuration is suitable for small-scale networks because it does not require the cooperation of a controller. However, it does not support bandwidth reservation. Method 2. Path computation by the ingress using a constrained shortest path first algorithm. The computed paths support bandwidth reservation but are only locally optimal. Method 3. Path computation by controller. The computation process is as follows. 1. After IGP and SR data is configured on the forwarder, the IGP completes topology discovery and label generation. 2. The forwarder reports topology and label information to the controller through BGP-LS. 3. The controller completes path computation. 4. The controller delivers the computed path information to the forwarder through netconf. 5. The forwarder generates tunnel configuration. SRTE tunnels generated by a controller have the following advantages. First, the controller supports bandwidth computation and resource reservation, and can therefore compute a globally optimal path. Second, the controller can cooperate with network applications. Upon receiving an application-generated requirement, the controller can quickly respond and compute a network forwarding path that meets the requirement in order to achieve a service-driven network. Third, the controller does not require a lot of manual tunnel configurations, resulting in tunnels that are much more suitable for large-scale networks. After SR tunnels are established, service traffic needs to be steered to the tunnels in a process called traffic steering. Because SRBE tunnels do not have tunnel interfaces, the traffic steering mode of SRBE is different from that of SRTE. SRBE supports 3 traffic steering modes, whereas SRTE supports 4. Here's a more in-depth look at the traffic steering modes supported by SRBE. The first mode is based on tunnel policies, and it requires you to apply a tunnel type priority-based policy to select SRBE tunnels. The second mode requires you to specify the next hop of static route as the destination address of an SRBE tunnel, and configure the route to recurse to the SRBE tunnel based on the next hop. The third mode requires you to configure public IP route, such as a BGP route, to recurse to an SRBE tunnel based on the next hop of the route. So, what are the traffic steering modes supported by SRTE? The first mode is based on tunnel policies. It requires you to apply a tunnel type priority-based policy to select SRTE tunnels, or a tunnel binding policy to bind SRTE tunnels. The second mode requires you to specify the outbound interface of static route as an SRTE tunnel interface. The third mode allows an IGP to use an auto route related to an SRTE tunnel, which is functioning as a logical link to compute a path. The outbound interface of the route is set to an SRTE tunnel interface. The fourth mode is policy-based routing. In this mode, the outbound interface in an apply clause is used as an SRTE tunnel interface. Routes and services that can recurse to SR tunnels include static routes, public BGP routes, and L3 VPN, VPLs, and EVPN services. Their forwarding processes are similar. Here, L3 VPN services are used as an example to describe the route advertisement process and data forwarding process. First, let's see how a public network tunnel is established. IGP and IGP-SR must be configured on the public network to establish an SRBE or SRTE tunnel. Then CE2 advertises a VPN route to PE2. After receiving the route, PE2 converts it to a BGP VPN v4 route and advertises the route to PE1 through the BGP peer relationship. PE1 links the route to the routing table of the corresponding VPN instance on CE1 and advertises the route to CE1. Through this method, CE1 obtains the route of CE2. In the route recursion phase, you can configure a tunnel policy on PE1 so that the SRBE or SRTE tunnel is preferentially selected. Now we can move on to the data forwarding process. Assume that an SRBE LSP exists on a public network. The LSP is established as follows. PE2 advertises a label, for example, 36,100 to PE2. P2 advertises the label, for example, 26,100 to P1. Then P1 advertises a label, for example, 16,100 to PE1. In this way, an LSP is formed. Assume that a common IP packet is transmitted from CE1 to CE2. After arriving at PE1, the packet is encapsulated with an VPN label that is allocated by BGP. Then the packet is encapsulated with an SRB label, that is, label 16,100, advertises by PE1 to PE1. After the encapsulation is complete, the packet is forwarded to P1. On P1, a label swap operation is performed, changing the outer label 16,100 to 26,100 while keeping the other labels unchanged. Similarly, on P2, the outer label 26,100 is changed to 36,100, and the other labels remain unchanged. Then P2 forwards the packet to PE2. After receiving the packet, PE2 removes the outer SRB label 36,100 that is advertised by itself, searches the routing table of the corresponding VPN instance based on the VPN label, removes the VPN label, and then forwards the packet to the VPN instance. P2 is the penultimate hop of the SRB tunnel. If penultimate hop popping is configured on P2, P2 removes the outer SRBE label 36,100 before forwarding the packet to PE2, so that only the VPN label exists in the packet. Now let's move on to the process of L3 VPN service forwarding through an SRTE tunnel. The first step is to establish an SRTE tunnel. For example, an SRTE tunnel composed of adjacency sets. Assume that the adjacency sets of PE1 to P1, P1 to P2, and P2 to PE2 are 1001, 1002, and 1003 respectively. In this way, a label stack 1001, 1002, 1003 that represents an SRT tunnel is formed on PE1. Let's imagine that a common IP packet is transmitted from CE1 to CE2. After receiving the packet, PE1 encapsulates the VPN label and the complete label stack 1001, 1002, 1003 into the packet. Because label 1001 belongs to PE1 itself, PE1 removes this label when sending the encapsulated packet to P1. Therefore, only labels 1002 and 1003 exist in the packet. After receiving the packet, P1 detects that outer label 1002 is a local adjacency label distributed by itself. Therefore, P1 removes the outer label 1002 and forwards the packet through the outbound interface specified by this label. After P2 receives the packet, because the outer label 1003 is the local adjacency label distributed by itself, P2 removes the outer label 1003 and forwards the packet through the outbound interface specified by this label. Now, only a VPN label exists in the packet. After receiving the packet, PE2 searches the routing table of the corresponding VPN instance based on the VPN label and forwards the packet to the VPN instance on CE2. The packet forwarding process is now complete. In terms of reliability, SR supports topology-independent loop-free alternate fast reroute, or TILFA. Traditional protection topology, such as remote LFA or RLFA, has constraints on the network topology, and therefore cannot achieve 100% fault protection. Take the network topology shown in the figure as an example. Assume that the cost value of the C to D link is 1000, and the cost values of all other links are 10. For traffic transmission from A to F, the primary path is A to B to E to F. If the B to E link is faulty, B switches traffic to the backup link B to C. However, if C does not detect the link fault between B and E, because the cost value of the C to D link is 1000, C considers that the optimal path to F passes through B. As a result, C sends the traffic to B, causing a forwarding failure. If TILFA is used, after detecting a link fault between B and E, B adds a new explicit label stack, such as a stack consisting of the adjacency set 304 of C to D and the node set 103 of C to the original packet. After the packet reaches C, C implements instructions according to the explicit label stack and forwards the packet to D. The optimal path from D to F is D to E to F. In this way, the packet can be forwarded successfully along the path. The differences between the two protection technologies are as follows. With RLFA, when a fault occurs, B considers that the shortest path to F passes through C, while C considers that the shortest path to F passes through B. B and C make decisions independently. With TILFA, B can add an explicit label stack on the packet. Because C does not have the right to make decisions, it can only forward the packet by executing instructions based on the explicit label stack. Next, let's discuss enter AS SRTE tunnels. Assume that there are two ASX and ASY. An IGP is used to establish an SRTE tunnel in each AS. The tunnels are named SRTE1 and SRTE2. Because inter-AS paths do not belong to the IGP area, the IGP cannot allocate seats to the paths. As a result, the ingress fails to perform complete path orchestration. The solution is to use a BGP extension to allocate seats to the inter-AS paths. BGP can allocate three types of seats. The first type is a peer adjacency seats that is unidirectional and allocated based on adjacencies. The second type is a peer node seat. For example, ASBR1 may allocate a peer node seat to ASBR2. The third type is a peer set seat that is allocated to a group of peers. For example, ASBR1 may allocate a peer set seat to ASBR2 and ASBR3 at the same time. The three types of seats can all participate in path orchestration. In this way, the ingress can use the label stack of SRTE1, the BGP allocated seat, and the label stack of SRTE2 to form a complete end-to-end or E-to-E SRTE tunnel. However, this method involves too many seats, which may exceed the hardware limit of devices. Therefore, a new type of seats, binding seat, is developed to address this issue. After a binding seat is allocated to SRTE2, an inter-AS E-to-E SRTE tunnel can be formed based on the binding seat, BGP allocated seat, and the label stack of SRTE1. This enables the ingress to form an inter-AS E-to-E SRTE tunnel based on these seats. Transit nodes do not need to maintain tunnel status. Therefore, there is not much pressure on the control plane. This provides SRTE with a major advantage over RSVPTE, making it much more suitable for large-scale networks. How can existing networks transform into SR networks? As we all know, existing networks generally contain a large number of services and are extremely difficult to upgrade on a large scale. Most existing networks require a smooth evolution. As a new technology, SR can only be fully utilized by upgrading existing devices. In the transition phase, SR needs to interwork with legacy networks. The most common transition technology is SR-LDP interworking. SR-LDP interworking enables SR and LDP to work together on the same network. With this technology, an SR network can be connected to an LDP network, implementing MPLS forwarding between the two. This topology is used as an example to describe SR-LDP interworking. Assume that the SR domain is on the left and the LDP domain is on the right. The inter-domain device needs to support both SR and LDP. SR-LDP interworking involves the following two directions. The first direction is from the SR domain to the LDP domain. The technology used for this direction is called mapping server. Mapping server can be configured on any device in the SR domain to allocate seats to the prefix in the LDP domain. Then seats are mapped to LDP labels based on the prefixes in the form of prefix seat LDP label. When the packet is forwarded from the SR domain to device 2, the SID is converted to an LDP label identifiable to the LDP domain. In this way, the packet is successfully forwarded in the right direction. The other direction is from the LDP domain to the SR domain. The proxy LDP ingress technology is used for this direction. The proxy LDP egress is generally an inter-domain device. It can allocate LDP labels to prefixes in the SR domain. Then LDP labels are mapped to SIDs based on these prefixes. In the form of prefix LDP label, SID. When the packet is forwarded from the LDP domain to the SR domain, the LDP label is converted to an SID identifiable to the SR domain. In this way, the packet is successfully forwarded in the right direction. SR-LDP interworking is thus implemented through the two technologies. If all devices support SR, you can perform the following steps to upgrade an LDP network to an SR network. Step 1. Run SR on all the devices to establish SR tunnels. Step 2. Configure tunnel policies on all the devices so that the SR tunnels are preferentially selected. Step 3. Disable LDP on all the devices. You can upgrade an RSVPT network to an SRT network using the same method.